Here are the solutions to the 3.2 activity on the mean value theorem. The first problem says your calculus book was dropped off a 144 foot high building and its position is given by s of t equals negative 16t squared plus 144, where time is in seconds. Find the average velocity on the time interval from t equals 1 to t equals 3. So average velocity is always a change in position divided by a change in time. So in this case, that change in position will be s of 3 minus s of 1 divided by that change in time, which is 3 minus 1. We calculate those using the position function, and we get an average velocity of negative 64 feet per second. Since the book has been dropped and falling down, this makes sense. The second question says, the average velocity is the slope of what type of line? The average velocity is always the slope of a secant line. What does the mean value theorem allow you to conclude about this situation? It allows us to conclude that the mean value theorem in words says that the slope of the tangent line is equal to the slope of the secant line at some point. And so that says that at some time in 1,3, the slope of the tangent line, which is the instantaneous velocity, this is the slope of the tangent, equals the average velocity. Find the time that satisfies the conclusion of the mean value theorem. Well, the derivative of position is velocity. So instantaneous velocity in this context is given by negative 32t. We want to know when that's going to be equal to 64, and that is going to happen at t equals 2 seconds. And this says that, in other words, the slope of the tangent line to s of t at t equals 2 equals the slope of the secant line between 3, 0 and 1, 128. Okay, the second question says, consider this function f of x equals 2x minus 1 to the negative 2. Show that there is no value of c in 0, 1 such that f of 1 minus f of 0 equals f prime of c times 1 minus 0. Why doesn't this contradict the mean value theorem? Okay, well, if we could apply the mean value theorem here, really here would be the conclusion of it, right? Oops, that's definitely not an M. Sorry, let me try that again. Here would be the conclusion of the mean value theorem. It would be that f prime of c is equal to f of 1 minus f of 0 over 1 minus 0, which is really exactly what's written here, just having divided both sides by 1 minus 0. Sorry, multiplied both sides by 1 minus 0. All right. So if this was true, f of 1 is 1 to the negative second power, which is 1. F of 0 is negative 1 to the negative second power, which is also 1. So f prime of c would have to equal 1 minus 1 over 1 minus 0, which is 0. Okay, let's see if that happens. Let's take the derivative of this function. We need the chain rule. We get negative 2 times 2x minus 1 to the negative third power times the derivative of what's inside, which is 2. We rewrite that. F prime looks like negative 4 over 2x minus 1 quantity cubed. But f prime is never equal to 0, so I cannot satisfy this right here. And so I can't find a c. Up here we were able to find a time t where that satisfies the conclusion of the mean value theorem. Here I can't find a c to satisfy the conclusion of the mean value theorem. So why is this not an issue, or why doesn't this contradict the mean value theorem? It doesn't contradict it because our original function has a discontinuity when the denominator is equal to 0, which happens at x equals 1/2. So it's not continuous on the open interval from 0 to 1, and that is one of the conditions that is needed to apply the mean value theorem. So when we're applying these theorems, intermediate value theorem, Rolle's theorem, mean value theorem, we need to think about whether we've satisfied the conditions of the theorem. Okay, final question. Show that 2x minus 1 minus sine x has exactly one real root. All right, there was an example like this in the introduction video. This is usually a challenging topic, so I thought we'd walk through this one together as well. Okay, so what do we have to do? First, we have to, our first job is that we have to establish at least one root. And so we want to one root of, let's think of the function as this. F of x is 2x minus 1 minus sine x. And to do this, we use the intermediate value theorem. Okay, so that means I want to find a spot where when I evaluate this function, it lives below the x-axis, and another time where I evaluate this function and it lives above the x-axis. Okay, well, I'm going to think about times that I can evaluate the sine function really easily. One of the things I can find easily is f of 0. F of 0 is 2 times 0 minus 1 minus sine of 0. But that's 0 minus 1 minus sine of 0, which is 0. So that is just negative 1. Okay, another place, I could go to pi over 2, where I know the value of sine. Let's see what happens if we go do that. We get 2 times pi over 2 minus 1 minus sine of pi over 2. So what is this? That looks like pi minus 1 sine of pi over 2. Well, sine reaches a maximum at pi over 2 is 1. So this looks like pi minus 2. Well, pi minus 2, what do I know about that? Pi is 3.14 something. Take 2 away from that. This is approximately 1.1425, etc. But more importantly, this is larger than 0. So at 0, our function is below the x-axis. At pi over 2, it is above the x-axis, which means that somewhere in between pi over 2, it must hit the x-axis. So the intermediate value theorem says that there exists a point, call it B, in the interval from 0 to pi over 2, such that f of b is equal to 0. What is it really saying in pictures? Well, we know at 0, the output of this function is negative 1. At pi over 2, the output of this function is slightly larger than 1. Our function is continuous. 2x minus 1 and sine x are continuous everywhere, so the function is continuous everywhere. That's why we can apply the mean value theorem. We know that somewhere this must cross the x-axis. Okay, so that was our first job. We established that there is at least one root. And now our second job is to show that b is the only root. Okay, how are we going to do that? Well, there's infinitely many other options to be roots, right? We can't eliminate them all. So how we do this is we assume there is a second root, and then we show that that leads to something that is completely false. So assume a is a second root of f of x. Or in other words, assume that f of a is also equal to 0. And we want that to lead to something that's false. Okay, so now what do we know? Now we know that f of a is equal to 0, which is equal to f of b. Our function is continuous and differentiable. So f of x is continuous and differentiable. And it doesn't really matter, but let's assume that a is smaller than b. The same argument holds either way, but just for sake of notation. Okay, so now we have all of the conditions we need to apply Rolle's theorem. And what does Rolle's theorem do? Rolle's theorem holds and tells us that f prime of c is equal to, is equal to 0 for some c in the interval a, b. Okay, well, let's explore f prime of c being equal to 0. So let's go back and remember f of x was 2x minus 1 minus sine x. So f prime of x is equal to 2. The derivative of sine is cosine, so 2 minus cosine of x. Okay, what do we know about cosine? Well, cosine of x we know strictly lives between negative 1 and 1, which means negative cosine of x also strictly, we would technically switch the inequality here, lives between negative 1 and 1, which means if we add 2 everywhere here, 2 plus 1 is greater than or equal to 2 minus cosine is greater than or equal to 2 minus 1. So 2 minus cosine of x is greater than or equal to 1 and less than or equal to 3. That was a lot. You could have argued that more efficiently by just saying you know the smallest cosine, negative cosine of x ever gets is negative 1. All we need to know is that this thing is always positive. But there's supposed to be some place where f prime of c equals 0. So because f prime of x is positive, this work comes up here. F prime of c does not equal 0. Which means this can't happen. F of a equals 0 equals f of b. This cannot be true. So which means that this cannot be true because we've already established it's definitely true for b. And so that means that a, there is no second root. So a cannot exist. And only root is in the interval from 0 to pi over 2. Okay, we established there is at least one root, called it b. We said, hey, could there be another one? If there's another one, Rolle's theorem has to hold. Well, if Rolle's theorem holds, the derivative has to be equal to 0, but the derivative is always positive. So Rolle's theorem can't hold, which means that second root can't exist, which means we can't have any other roots. And so this root a cannot exist, and the only root is in 0 to pi over 2. All right, there are the activity solutions for section 3.2. See if you can go ahead and get started on the homework in the textbook.